Today we're going to start talking about sequences, and this leads to a lot of other things that we're going to learn in calculus. All right, so we're going to start really simple today, okay, with just listing the terms of sequence. So a sequence is just a list of numbers. All right, so if we have this formula a sub n and we use the little subscript right here to represent the term number. So if we want to find a sub 1, then that just means we're going to put 1 right here into our formula for the first term of the sequence. So this would be 3 plus -1 to the first power. Well, that would be -1 to the first. So that'd be -1, and 3 plus -1 would give you 2. So that's the first term of our sequence. And then the second term, so a sub 2 would be 3 plus -1 squared. And then that becomes 1, and 3 plus 1 is 4. And then a sub 3 would be 3 plus -1 to the third power. And so that would be -1. So this one would be 2. And then a to the fourth would be 3 plus -1 to the fourth. That would be 1. So this becomes 4. And so you notice like the pattern is it's just going back and forth between 2, 4, 2, 4. And even a to the fifth, it's going to go back to 2. And so this is going to be 3 plus -1 to the fifth, and that's going to give you 2. So our sequence is 2, 4, 2, 4, 2, and then dot, 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 because this just keeps going forever, okay? And so it's just alternating 2, 4, 2, 4, okay? Let's go to the next one. So our formula for the terms of the sequence are a sub n is equal to n over 1 minus 2n. So a sub 1 would be 1 over, and then 1 minus 2 times 1. So that would be 1 over -1, which gives you -1. A sub 2 would give you 2, because n is 2, over 1 minus 2 times 2. So that would be 2 over 1 minus 4, which gives you -3. So this one is -2/3. A sub 3 would be 3 over 1 minus 2 times 3. And that would be 3 over 1 minus 5, which would be, 1 minus 5, which would be, 1 minus 6, which would be -5. So this is -3/5. And a sub 4 is 4 over 1 minus 2 times 4. And so that would be 4 over -7, or -4/7. And even with these, like you start to realize, okay, this is 2, 3, 4. So the numerators are going up by 1, right? And the denominators are going up by 2. So I'm thinking the next one's going to be -5 5/9. And if we try it, a sub 5. So we're going to be looking for patterns like this, okay? So the fifth term of the sequence would be 5 over 1 minus 2 times 5. And that would be 5 over 1 minus 10, which would be -9. So yes, it's -5/9. Kind of like what we predicted, just looking at the terms of the sequence. So that means we have -1, and then comma, -2/3, and then -3/5, and then -4/7, and then -5/9, and then comma, and then dot, dot, dot. And so that's that one. Okay, so how about this next one right here? Okay, a sub n is equal to n squared over 2 to the n minus 1. Okay, so a sub 1 would be 1 squared over 2 to the first minus 1. So that'd be 1 over, this would be 2 minus 1, which is 1. That would give you 1. The second term would be 2 squared over 2 to the second power minus 1. So this would be 4 over 2 squared would be 4, minus 1 would be 3. So that's 4/3. And then the third term would be 3 squared over 2 cubed minus 1. And so that would give you 9 over 2 cubed, that'd be 8. 8 minus 1 is 7. And then the next one, the fourth one, would be 4 squared over 2 to the fourth minus 1. And so this would be 16 over, this would be 16 minus 1, which would be 15. And then the last one for this would be 5 squared over 2 to the 5th minus 1. So 5 squared is 25. 2 to the 5th is 32 minus 1, which would be 31. And so it would be 1 over 1. And it's helpful to look at like this, okay? 1 over 1, comma, 4/3. It's if one of them turns out to be a number, sometimes it's good to just look at them as being fractions and look for a pattern. So 1 over 1, 4 over 3, 9 over 7, 16 over 15, 25 over 31, comma, dot, dot, dot. So, you know, when if I gave you the sequence, how would you write the formula? That's where we're going with this, okay? Is if you look, okay, these are all perfect squares. You notice that that's where the n squared comes from. And look at the pattern here. Okay, so we really don't see a pattern, but you got to know your powers of 2. So this is 1 less than 32, 1 less than 16, 1 less than 8, 1 less than 4, 1 less than 2. So these are 1 less than powers of 2. And that's why it's 2 to the power minus 1. Okay. All right, so let's go to the next part D of this. So for part D, we want to list the 5 terms of the recursively defined sequence with a sub 1 equals 25. So this, if you look at this, okay, this is the first one. This is a term plus 1. So that this would be the next term. After you know one, you can get the next one. So a sub 2 or a sub 1 is 25. Let's put that one because that is the first term. Okay, to get the second term, what we have to do is put 1 in for n. So that'd be 1 plus 1. And so this would be 1. So the second term is a sub 1 minus 5. So this is called recursively because you have to know the previous term in order to get the next term. So that means this is 25 minus 5, which would be 20. And then a sub 3, okay, so now we're putting we're putting 2 in for n, which makes this 3. And so this means to be the second term. So this is always the term before this one. So if this is a sub 3, this is going to be a sub 2 minus 5. Well, a sub 2 is 20. So this would be 20 minus 5 or 15. A sub 4. Okay, so if a sub 4, we're putting 3 in for n, and that makes this 3. So a sub 3 minus 5. Well, that would be 15 minus 5 or 10. And then a sub 5. A sub 5, if we're finding a sub 5, that means n is 4. And so we're finding that's equal to a sub 4 minus 5. And so that would be 10 minus 5, which is 5. So our sequence is 25, 20, 15, 10, comma 5, comma, dot, dot, dot. And if you look, okay, we started with 25. That was the first term, right? And we're subtracting 5 each time, right? And so you can get the next term by saying, okay, we're just taking the term and subtracting 5 from the previous one to get the next one. And that's what this is saying. All right, let's go to the next one. So for these examples, graphing the terms of a sequence, we're going to do this with technology. So we're going to use your graphing calculator, and I'm going to show you how to graph the first 10 terms of a sub n is equal to n squared plus 1. So I'm going to show you how to put this in your graphing calculator. All right, so let me go to the graphing calculator and I'll show you that. So to graph this first sequence, a sub n is equal to n squared plus 1, what we first need to do is press the mode button, and we need to switch modes. So we're normally in the function mode, but we need to switch over here to the sequence mode. So go down and across, and we need to highlight sequence. And then when we go to y equals, you take a look here, and we want the type of the sequence. We want sequence of values for n, okay? And we want our n min to be 1, and then our u sub n, that's actually going to be our a sub n, okay? And just in the calculator, they call it u sub n, or u of n. And then we want that to be n squared, and then plus 1. And then for our settings, we need to go up here to our window. And okay, so when we put 1 in here, we get 1 squared plus 1, which would be 2.
And then when we put 10, because that's going to be the last one because we want to graph the first 10, we would have 10 squared plus 1, okay, and that would be 101. So we probably want to be above 100 and, above 100 for our Y max. So we go to our window. So this is a little bit different than when we have the function window. We want our in min to be 1. We want our in max to be 10 because we're going to stop this at 10. We only want to graph the first 10 terms, okay? And then we come down here and plot start is 1. That's fine. Plot step is 1. That's fine. X min, we want probably start that at 0. And our X max is 10 because on the X axis, that's going to be our in value. So 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 10. X scale 1. Our Y min, I would put that at 0. And our Y max, I would put it like at 105 because we know it's the last term is going to be 101. Okay. And then Y scale, I'd probably go by 10s or 20s. Okay. And then we go to press graph. And this is what the graph looks like. Now take a look. There's only a term at 1, at 2, at 3, at 4, 5, 6, 7, 8, 9, and then this last one at 10. Okay, because this is a sequence. So we don't have values in between. All right. So that's how you graph it. I just want you to graph into your calculator, and that's all you need to do. Okay.
Next, let's graph the 10 terms of a sub n is equal to negative 32 times 0.5 raised to the n minus 1 power. So let's go to our graphing calculator, and I'll show you how to do that.
Next one, we have a sub n is equal to negative 32 times 0.5 raised to the n minus 1 power. So one thing you can do is put in the first value and just see where we're going to land. So negative 32 times and then 0.5 raised to the 0 power. And we should know that that's going to be negative 32. And then negative 32 and then times 0.5. And then raised to the, and the in value is 10, right? Because we're going to do the first 10 terms. So this is going to be a power of 9. And so this is telling us, okay, so our window for our outputs, we want to go, below negative 32 and probably up to like 0. Okay, so that's why I was doing this to figure out kind of where this lands, and we may need to adjust the window settings. So let's go back to our y equals, clear out what our sequence, that first original sequence is, and let's type in negative 32, and then a parenthesis, and then 0.5, and then raise to the n minus 1. I notice I'm using the x key because that's what we use for all the function variables, the normal function variables. Okay, and then go to our window, and again, in min 1, in max 10. These starts are fine. X min 0, X max 10, X scale 1. Y min though, Y min we want to go lower because remember it was from negative 32 to about negative 0. Really close to 0. So negative 0.0625, I think. So let's make this one like negative 40. And then let's make our Y max 0. And let's graph that. Well, let's do our Y scale. Yeah, 10's good. 10 or 5. And let's go ahead and graph it. And so it looks like this. Now, this is a feature that's going to be really important. You see over here on the right-hand side, it's flattening out. Okay? That means we're getting closer and closer to, this is the first term, second term, third term, fourth term. And notice the difference between them is getting smaller each time, right? So that means the value is getting closer and closer. It's approaching something, right? It's kind of like, if you think about it, a horizontal asymptote. So the nth term is getting closer and closer to, it looks like 0, okay? All right, so let's go graph this last one, all right?
And then finally, let's look at the first 10 terms of a sub n is equal to 3n plus 5 over n minus 2. Let's graph that one on the graphing calculator, and we'll come back and look at that.
So for this last example, there's actually a typo. The denominator actually can't be n minus 2 because if n was 2, right, we're going to put 1 in and 2. That would cause the denominator to be 0. So it should be n plus 2, not n minus 2. So what we want to do is let's figure out, okay, what are the values, right, for the first term of the sequence and then the 10th term, right? So this would be 3 times 1 and then plus 5. And then down here, let's do not n, I'm sorry, 1 plus 2. Okay, so right about 3, right? Okay, and then let's do the 10th one. So that would be, pull up our fraction bar, and then 3 times 10, and then plus 5, and then over, and then be 10 plus 2. And so 2.9, so roughly 3. Okay, so let's go to y equals, all right, or sorry, roughly 3, and this is pretty close to 3 also, right? So y equals, all right, and for this we're going to type in our fraction and 3n plus 5, and our denominator will be n plus 2. Okay, and then for our window, again, we're not going to change these because we want to step it up by 1, and we're going to go 1 to 10, and 0 to 10 for our x min and x max. And then y min, okay, so we want to switch this, right? So we want to switch this to, I would say go from like 0 to 5. Because remember it was about 3. And then scale, I would go by ones. And let's take a look at this graph. Okay, so see it's kind of barely coming up, right? And then it's flattening out over here. Okay, so that means that as we go further and further out, it really looks like the sequence is approaching some value. The term of the sequence, the nth term, is getting closer and closer to one particular value. That's what you're seeing is this flattening out over here. Okay? And that's how you graph these on the graphing calculator, okay?
So if you look at this one, okay, this example 3, we're writing the next terms of the sequence. So this is where you have to start looking for patterns that you see, okay? So you're gonna look for, okay, are we subtracting the same amount? Are we adding the same amount? Are we multiplying by the same amount? So write the next 2 terms of the sequence and describe the pattern you used to find these terms. Okay, so 26, 21, 16, 11, 6. If you look at this, we're consistently reducing it, or we're subtracting 5. So 26 minus 5 is 21. 21 minus 5 is 16. 16 minus 5 is 11. So this pattern's holding, right? We're subtracting 5. So that means the next term, if we take 6 and subtract 5, the next term would give us 1. And then subtract 5 from that, and the next term would be -4. So these would be the next 2 terms of the sequence. And what we notice is we're subtracting 5 from the previous term. So that's what we're doing. We're subtract 5 from the previous term. Okay, how about this one? 3, then 6, and then 12, and then 24. So if we try to add, right, we're adding 3, but then we're not adding 3 from the second term to the third term, right? And so some of you might be seeing, okay, yeah, I can see this. We're just multiplying by 2. So 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. So we're multiplying the previous term by 2. So that means the next 2 terms, well, 24 times 2 would be 48. And 48 times 2 is 96. So those are the next 2 terms of the sequence. And what we're doing is we multiply the previous term by 5. Not by 5, sorry, by 2. Okay. All right. So this next one, okay, this we can see this as, okay, this is 1/1, right? And so we could write this as 1/1 because that way it gives us fractions for each one of them, okay? And so you look at this, okay, 1, 5, 25, 125. So you're looking, okay, I'm multiplying by 5 each time, right? And then 1, and then 3, and then 9, and then 27. Oh, I'm multiplying by 3. But take a look. The first term is positive. The next term is negative, positive, negative. So that happens when you're multiplying by a negative. Because if you have a negative times a positive, you're going to get a negative. But when you multiply that same negative number, you're going to get a positive. And so it's going to alternate signs. All right. So what we're doing here is we're multiplying by -3/5 each time, not just 3/5. Okay. So if we multiply this last term by -3/5, we would wind up with -27 times -3, which is 81 over, and then 125 times 5 would be 625. and it's positive because I'm taking this previous number and multiplying it by negative 3/5. And then if I take this next term and multiply it by negative 3/5, well, multiplying this by negative 3/5 would give me negative, and it would be 243 over 3,125. 3,125. And so what we're doing is we're multiplying multiply the previous term by negative 3/5. All right, and that's how you do that. So the next thing I want to talk to you about and teach you about is factorials. Okay, and when we see an exclamation point in math, it actually means factorial. And what it means is if we're finding in factorial, all right, in exclamation point, right, that means 1 times 2 times 3 times 4. So you're going up by 1 and you're multiplying each time, and you're going up all the way until you reach whatever n is. Okay. And then there's one where what is 0 factorial, and we need to understand what 0 factorial is. It's not 0, it's actually 1. Okay. And then from this, we can tell that 1 factorial is 1. 2 factorial would mean 1 times 2. 3 factorial would be means 1 times 2 times 3, and so on. Okay. Now, factorials are like exponents. Okay, I don't say they are exponents, but they're like exponents, and how we write them really matters. So like 2x cubed means you're only cubing the x. 2x in parentheses cubing that means something different than this one, right? So same thing with factorials. So 2 in factorial means 2 times in factorial. So that'd be 2 and then times 1 times 2 times 3 times 4 and all the way up until the in factorial. So if this is 2 times 5 factorial, we would write 2 times 1 times 2 times 3 times 4 times 5. Okay. If we did 2 in factorial, okay, whatever n is, let's say 5, that means we'd have to go up to if n was 5, we'd have to do 10 factorial. And that would mean 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10, all the way up until we reach that number 2n. Okay. All right, so with this, how do you simplify? Okay, so the simplest way is to, okay, and I'm going to show you the long way so that we can do it the short way. So 6 factorial, what does it mean? Well, it means 1 times 2 times 3 times 4 times 5 times 6, or I'm going to write it actually backwards. 6 times 5 times 4 times 3 times 2 times 1 over 4 factorial, which would be 4 times 3 times 2 times 1. And I want you to notice something, okay? The 4 times 3 times 2 times 1, it's going to cancel in the numerator and the denominator, right? So what we're left with is really 6 times 5. Now, a way we can do this is whichever has the higher factorial, we could write that one. So we could write this as 6 times 5. And we know the rest would be 4 factorial, right? Because 4 times 3 times 2 times 1 is really this 4 factorial over 4 factorial. And then we can just cancel our 4 factorials and we're left with 6 times 5, which is 30. So 6 factorial divided by 4 factorial is the number 30. And that's how you do them, okay? So let's do the next problem. So how do we simplify something like this that has an n in it, right? So remember that if we start with 2n plus 5, we start with that number, we're going to go down by 1 and multiply that number, and then reduce that one by 1 and multiply by that number. So that makes this 2n plus 5. We would have, this is equivalent to 2n plus 5. And watch what happens. And this one's the larger one of these two, right? Because they're both 2n, but this one's plus 5. This one's larger. So 2n plus 5, and then times, and we're going to reduce that by 1. So 2n plus 4. And then times, and reduce that one by 1. So that'd be 2n plus 3. And then reduce that one by 1. And we'd have 2n plus 2. And then we reduce that, right? And we keep going. And so we could actually make this one a factorial. So 2n plus 2 factorial. Now, why is that beneficial? Well, it's because the denominator is 2n plus 2. And that's why I stopped right there. So I wrote all of them up until we got the 2n plus 2. And so this would be 2n plus 2 factorial. So what happens is this 2n plus 2 factorial and this 2n plus 2 factorial cancel. And what you're left with is 2n plus 5 times 2n plus 4 times 2n plus 3. This is going to happen a lot in this unit where you're canceling factorials like this. And so you always want to start with the biggest one and write them all the way down until you reach this one right here. Okay. Or vice versa, if this was the bigger one. Okay. So for this one, we want to simplify n minus 2 factorial over n plus 1 factorial. Okay, so n plus 1 is going to be larger because I can start reducing this by 1 each time, right? And so I want to start with this one. And so I'm going to write my fraction bar and I'm going to leave the n minus 2 factorial on top. And so we're going to multiply by n plus 1. And then we're going to reduce that by 1, which would be n plus 0 or just n. And then we're going to reduce that one by 1. So that would be n minus 1. And then we're going to reduce that one by 1. So then we'd have n minus 2. And now we've met this, right? And we'd keep doing that forever. And so we'd have a factorial, right? So this n minus 2 factorial in the numerator cancels with this n minus 2 factorial in the denominator. And so what we have left is, this is the same as 1 over n plus 1 times n minus 1. And that's how you simplify these. Okay. I would probably rewrite this one and put the n first. So 1 over n times n plus 1 times n minus 1. Would you have to? No, you wouldn't have to, but I think that's just a little bit of a cleaner way of showing it. All right. So we're going to look at limits of sequences next. Okay. So we're really going to look at this limiting idea throughout this unit. And then a lot of sequences that approach limiting values, okay, we say that those converge. All right. So for instance, this one right here, a sub n is equal to 1 over 2 to the n. All right. So our denominator is getting bigger and bigger and bigger and bigger every time we put 1, 2, 3 in, right? And in are the positive integers, 1, 2, 3, okay, or the natural numbers, some people call them. All right. So the denominator keeps getting smaller and smaller and smaller. That means this limit is getting closer. This value of the term is getting closer and closer and closer to being 0 the further we go out. Okay. So the limit of a sequence, we can write the limit of the sequence as n goes to infinity of L, and it's equal to some L. All right. And if that limit exists, then we say the sequence converges. If it doesn't, then we say it diverges. All right. And then we have some other limits. So a couple theorems that I want to talk about down here on properties. So let me slide this up. So if we know a function, a specific function, now a function is a real value function, which means we can put any real number in, unlike a sequence, a term of a sequence in that we can only put 1, 2, 3, 4, 5 in for like n. So if we know the function is equal to L, and we know that the function is the same as the term formula for every positive. Now the function actually would have more values, right? Because you could put in like 1.5 and 1.3, and you could put other values in. But if we know that the function and the term formula a sub n is the same for every positive integer, then we can say that that limit of that sequence is equal to L. So we can treat these like kind of like functions, is basically what it says. And then these properties, if we know one sequence, the limit as n goes to infinity is L, and another sequence is K, then what we can do, this is just like other limit properties. We can take the limit of each one individually and add or subtract them together, okay? Same thing here. If we have a constant C times a sequence a sub n, then what we can do is multiply that constant times the limit as n approaches infinity. So let me write this one out. So this one we can do individually, the limit of as n approaches infinity individually. This one, what we're really doing here is we're doing C times the limit as n goes to infinity of a sub n. And so this becomes L, and it would be C times L. So here, what we're doing with the product is, okay, if we take the limit as n approaches infinity of two different sequences, we can find the limit of each one and multiply them together. That's what this says. Same thing with division, as long as the denominator sequence isn't 0, okay? And k can't be 0, so the limit can't be 0. All right? All right, so that is how we do properties of limits. So let's go and do let's find some limits of some of these sequences. So some of these sequences are from the first page of sequences that we found the first 5 terms. So I'm going to go back to that first page. And okay, so realizing this one was a sub 1 is 2, and a sub 2 is 4, and a sub 3 is 2, and a sub 4 is 4, and a sub 5 was 2. Okay, so we look at this, and these values aren't approaching anything, right? They're just bouncing between 2 and 4. So it's just, we say it would be alternating. So this is alternating between 2 and 4, 2, 4, 2, 4. Okay, so we would say the sequence is alternating between 2 and 4, and it would diverge. So the sequence, it's not approaching one value, is alternating between 2 and 4. And so the sequence diverges. Okay, so for this next one, okay, and let me slide this up a little bit. Okay, so for this next one, let's take a look at this one, because this one it wasn't doing something like this, right? So let's find the limit. Let's try to even find the limit as n approaches infinity of a sub n. That's equivalent to the limit as n approaches infinity of n over 1 minus 2n. And so what's causing the growth in the numerator, because we're going to infinity, we can look at the growth factor here. So like n and negative 2n. So we can compare those two and rewrite this as the limit as n goes to infinity. So really this one is insignificant when n's going to infinity. All right. And we're going to look at the limit as n goes to infinity of n over negative 2n. And so our you can think of our n's as canceling here. So that'd be the limit as n goes to infinity of negative 1/2. So that means this limit comes out to be negative 1/2 because there's no n, right? So that means, because we got a limit value here, that means this converges. And as we go further and further out, that last term, right? That last term is getting closer and closer and closer and closer to negative 1/2. Okay, so we say the sequence converges. All right. And then for this one, let's take a look at this one. So let me slide my paper up a little bit. So for this one, we're going to take a look at the limit as n goes to infinity of a sub n. That's equivalent to the limit as n approaches infinity of n squared over 2 to the n minus 1. And so in this one, what's controlling the growth in the numerator is n squared. What's controlling the growth in the denominator is 2 to the n. So this minus 1 is insignificant. So we could look at this limit as n approaches infinity. This is very much like how we did horizontal asymptotes, how we found the limits of horizontal asymptotes, okay? So this would be limit as n approaches infinity of n squared over 2 to the n. Okay, so we got to also realize, okay, which one of these types of functions grows faster, and it's exponentials. This is an exponential, and exponentials will always grow faster than power functions like this, n squared. So that means this is going to get way bigger than this one. So in this case, our denominator is getting big, right? So this is getting closer and closer and closer to 0. And so we say the limit, or this, not the limit, but the sequence converges to 0. Okay, and I should have said this one up here, the sequence converges to negative 1/2. And that's what we would say. Okay, let's do this last problem. So for this one, we're going to take, again, the limit as n goes to infinity of a sub n. And that would be the limit as n goes to infinity of 3n plus 2 over the square root of n squared plus 5. Okay, so again, we're going to look at, because n's going to infinity, we're going to look at what's causing the most growth in the numerator, and it's this 3n. The plus 2 is insignificant. We have a square root, and inside the square root, we have n squared plus 5. And so the plus 5 inside that square root is insignificant. So this would be the limit as n approaches infinity of 3n over the square root of n squared. And the square root of n squared is actually the absolute value of n. So that'd be the limit as n approaches infinity of 3n over the absolute value of n. But n is positive, right? All right, because n's going to infinity, so n's going to be positive. So we really don't need the absolute value. And then that means the n's cancel here. And so this winds up being 3. So we'd say the sequence converges to 3. And that's how we do, limits for sequences. Okay. And so if the limit exists, then we'd say the sequence converges to that number. And if it doesn't, then we'd say it diverges. The sequence diverges. All right. And that's all she wrote for this.